All right, physics reaction video number 55. I did a search for circuit examples, I think, and I'm realizing that if I do a filter for very, very recent, I do find more teachers. So that seems to work fine. So here we go.
Hi, everybody. Welcome back to another exciting episode of electricity.
Awesome.
So we're going to do a couple of series circuit examples in this session. All right, I just have a few circuits, and then we'll leave it at that. So we have a basic series circuit here, source of 20 volts, R1, R2, and R3, 200, 330.
So I'm looking at these numbers and wondering if they're meaningful. What do they add up to? So 530 plus 470. Oh, they add up to exactly 1,000. Okay, so that's where these numbers are coming from. But I like them being in the hundreds or even in the thousands, right? Because that's typically, if you grab a resistor out of a drawer, it's going to be, several hundred, if not in the thousands and multiple, tens of thousands. So I have found that I tend to do a lot of 1 ohm, 2 ohm type experiments or thought experiments or examples with students, but the internal resistance of batteries is on that order, and so you get yourself in trouble. Light bulbs, are single, double digits of resistance, and so you do a lot of that in labs. But if you're talking about grabbing something that looks like a resistor and it's called a resistor and you're putting it in the lab, it's going to be in the hundreds or thousands. So I think that's interesting. But yeah, it looks like this was picked because it adds up to 1,000. So we should have some relatively easy numbers to do, though. When they're finding the voltage drop across these, is that going to be nice round numbers? Maybe. All right, we'll get going.
470 ohms respectively. So let's find IT and let's find the voltage at each resistor. Okay, cool. We're going to do this the Ohm's law way, and we're going to do this the voltage divider rule method.
Oh,
all right. So just to
wow, now that's interesting. So the voltage divider rule is this fantastic thing. I have a colleague who uses the voltage divider rule every time they attack any problem. It's basically sort of codifying exactly how series resistors work. Typically, when there's just two, I think it's the effective resistance is R1 times R2 over R1 plus R2. And then to get the voltage, you use Ohm's law. But what's fascinating about it is very, very often you're using kind of like a control resistor in a circuit to then maybe a potentiometer to then understand what's happening in the rest of the circuit. So I'm curious to see how he does it. I wonder if he'll lump two of them together and then to figure out what the third is, or we'll see. I'm making some assumptions here.
Law. Let's find RT first. And we know RT is equal to R1 plus R2 plus R3,
nice,
which is 200 plus 330.
So the camera here, the two really interesting issues. It's got the autofocus, which you can see is happening every once in a while, but it's also got this lighting aperture problem going on where the paper is super, super bright when it's like, oh, your hand is the dominant thing. I'm going to adjust my aperture so that your hand doesn't look too bad. And then the white paper just gets too bright. Then he moves his hand and the camera's like, oh my goodness, there's too many photons coming in. Let me adjust that. And so what I'm already seeing him doing is he gets his hand out of the way, right? So he moves his hand out of the way. And I think that ultimately it's quite legible. And I really love this double camera business, right? So, you can see his face. So where he's looking, let me think about this. He's looking to the left and looks like he's left-handed. Yeah, because the writing is not flipped. Okay, so yeah, so he's not mirrored, neither am I. All right, and so then, is he going to look up at the camera to verify that what's being shown? I'm always so curious about those logistics, right? And some of it matters, some of it doesn't. I'll be honest, when I'm doing videos for students, I don't bother with this because, frankly, it makes the videos huge comparatively. Well, hang on a second, but that's when I'm doing screen recording. If you record your screen and you just have a few mouse marks, they're not that large of screen recordings. But if you add your face, like I'm doing here, like these videos that I make, they're gigantic because I add my face all the time. But he's got a camera either way, so it probably doesn't matter for him. So that's really, really interesting.
Plus 470. Okay, and that equals 1K.
Guilty. Gosh, I was just talking about what he's looking at versus what the students are looking at. And so the way I have this working is I've got a big old monitor up here where you can see my mouse, and I've got another monitor down here where I have my screen recording software, and it kind of shows me what it looks like, and it shows me where my image is. And so when I was supposed to be saying, hey, look up at him up here, I was actually looking at the copy, and you couldn't see my mouse. Man, it's so hard to get it right all the time, right? And I gotta tell you, I'm not gonna go back and change it. That's kind of my philosophy, just plug on through. But it's interesting to see how easy it is to get that kind of stuff confused. So, bad job on me. While we're stopped, notice the beautiful lighting here. This works just fantastic when his hand is out of the way. It's super easy to read. I bet you we could even read it up here. In fact, you can see I guess this is the back of graph paper or something. You can actually see the lines through the graph paper basically everywhere. So this is really, really great lighting.
Ready? 1 kilo.
Nice.
So now, IT, we want to find the total current. We know that's E over RT. Total voltage over total resistance, which is 20 volts over 1K, and that gives us 20 milliamps. So we know now that current in this circuit, IT, is 20 milliamps.
Yeah, love it.
All right? Now, to find the voltage at each resistor, we will take, so to find VR1, we'll do IT times R1, because we know IT is also the current through R1, through R2, and through R3. So VR1 equals IT times R1, which is equal to 20 milliamps times 200 ohms. And that will give us a grand total of 4 volts. So we would take 20 milli times 200 ohms, and that gives us 4.
Wow! Look at that! I've never used that button. Huh? Man, that's cool. I kind of leaned forward because I wanted to see how he was doing the times 10 to the right, and he used milli. Man. I mean, I'm kind of torn, right? Like, it's super awesome. It's exactly what's on the page. Look at that. He doesn't have the parentheses, but still it works. Is it very clear to all the students that this is times 10 to the minus 3? And what other buttons are available? I don't own this calculator. I didn't even see what he did. Let's go back and see what we can figure out how he did that. Okay, let's play it again. Shift. Oh, okay. So it's shift something. We couldn't see it out of the screen. So you guys must be laughing at me. I've never used that. I'd love to hear about it, right? So it looks beautiful, gets it done. It doesn't, is it just a multiplier, or does it actually attach to the number before it? Like, if you had this in the denominator, would you have to put parentheses around it? Lots of, so many questions. But I love how he shows it in the camera. I really, really like that.
100 ohms, and that gives us 4 volts. Okay? So let's just get in the habit of just marking on our circuit as we go along. This circuit is a story.
So I'm just pausing again, thinking about language, right? So he has used a number of ways to talk about it. He said, what's the voltage of R1? What's the voltage at R1? I haven't heard him use the phrase the voltage drop across R1. And I bet you some of you are squirming, right? Like, it's not a voltage add, it's always with respect to something, right? And so at what point do we really get concerned about that? I mean, obviously his voltages are going to add up to 20. So the charge gains 20 volts and then loses, and it comes back home again. So that's going to add up just fine. hasn't bothered me the way he's done it, right? But notice that I noticed it, right? So he didn't use the word across, but I don't think there's just one answer here. He's being consistent, and I think that's the way more important thing to be with your students. And this might not be the circuit that really has you question those sorts of things. It's typically when you've got a like a Kirchhoff's law type circuit, where you really have to think like, wait a minute, what's going on here? This series circuits is pretty straightforward. So I'm just really attentive to the language, and I'm loving how consistent he's being.
That should make sense at the end of it all. VR2 will be IT times R2, which is 20 milli times 330, and that gives us
6.6
voltage of 20 milli times 330. So we have 6.6 volts. All right.
So, wow. So, I mean, my gut instinct, when I see these numbers, they look pretty similar to each other, right? They're all pretty close, but this is going to be a big jump, right? So this is going to be 9.4. I mean, almost 10, right? Which means that this gets almost half. I mean, of course, the numbers work out, but it's striking that I was thinking that our answers should have been close. So somehow I was interpreting 200, 330, and 470 as being in the vicinity of each other. But this guy's the hog, right? It's getting almost half of the voltage. Interesting.
And then we have VR3, which is IT times R3, and that gives us 20 milli times 470 ohms, okay? Which is 20 milli times 470 is 9.4 volts.
So he set this up. The numbers work out beautifully. There's no interesting round-off errors. Where would a round-off error have caused some problems? Frankly, it would have been way back here at this calculation of the milliamps. So if this was 460, this would have been ugly looking, right? He would have had to truncate this somewhere, 20.7 or something. And then, depending on how you do that round off here, this process might have produced 3 voltages that didn't quite add up to 20 if you don't carefully keep track of where your round off errors are. I call them round off errors, just call them round offs. So that's my question for you guys, is how important is it when you're getting started here, building these skill sets with your students, to avoid that? I'll be honest with you, check my blog post. When I do Kirchhoff's laws problems, I actually work really hard to choose problems where all of the arithmetic you can do in your head, everything is an integer, right? So I make it so that all of my resistors, all of my batteries, and all the currents are integers. Well, I can't just make that crap up, right? I can't just slap it on the page. I actually have to really carefully make adjustments until everything's an integer. So the amount of circuit analysis that I have to do just to build one of these things is quite complex. In fact, I'm using these massive algebraic solvers for me, 9 equations, 9 unknowns, and then I get some ugly fraction, then I analyze the fraction, I say, ooh, if I multiply everything by 7, I'm going to get some beautiful answers here. And so I work incredibly hard at that because I just want them to use their head, be able to quickly say, 1 volt, 2 volt, 1 volt, 2 volt. And so he did the same thing. He didn't have to work as hard because this problem is easy, but it kind of looked like, not gorgeous round numbers. I mean, these two especially, and the 6.6 and the 9.4s, but look at this. It's going to add up perfectly to 20. I mean, exactly, no round-off errors. So I'd love to hear from you guys about how you deal with that. When do you start with this? When should you stop, right? Should I not be doing that? I love it. I find class to be quite useful. Nobody's grabbing their calculators. We can just talk about stuff. So I'm super intrigued by that.
Okay. Now, we can also use Kirchhoff's voltage law to say that since since E minus VR1 minus VR2
Yeah, here he's doing it.
VR3 is equal to 0, we could say that VR3 is equal to E minus VR1 minus V.
So, I know a lot of left-handed people. I'm not left-handed, but I know a lot of left-handed people. And sometimes I joke with them about how they have to write sort of up here, and that gets the ink all over their hand. But I'm actually really fascinated about our societal choice to have our writing go from left to right, because left-handers, look what's happening here. He keeps adding more and more super interesting stuff, and we can't see it. So, if he were right-handed, we would already be able to see the left-hand side of what he is writing, and it would like be slowly revealing itself as it goes. And so if you're left-handed, you're talking, you can hear him, he's doing really good stuff, he's explaining it, and then it's going to be this big reveal when his hand finally gets out of the way. So does the fact that our writing go left to right, is it tied to the fact that the majority of people are right-handed? I never thought about that before.
R2. Which makes sense, right? If we know the sum of the three resistor voltages is equal to E, then we'll know that this voltage across R3 would be E minus VR1 minus VR2. Okay? Which would be 20 minus 4 minus 6.6.
And lo and behold,
Okay, which gives us 9.4.
ding!
All right? So just another way of doing it. So let's do this using the voltage divider rule method.
Yeah, I want to hear that.
Voltage divider rule. So we know that VR1 is equal to R1 over RT times E, which is 200
Cool.
over 1K
Whoa!
times 20. And that would be equal to...
So when he said voltage divider, I really had a very particular thing in mind 20 minutes ago. But I see what he's doing now. For series circuits, it's literally the voltage is divided among the resistors. And how much do you get? Well, how much you got, right? And so this is actually how I was thinking of doing this problem. Mathematically, it's the exact same work. He already had, so 200, what does he have here? 200 divided by 1K is this number times 20. So 200 divided by 1K times, wait a minute. Oh, okay. Yeah, no, it's different, sorry. So he took 20 divided by 1,000. And that's how you get this number here. Now he's doing 200 divided by 1,000, and then later multiplying by the 20. So it of course, it's the same thing, right? Of course, we're going to get the same answer, but it is a very, very different approach. I think that most students learn it this way first, but I find that when I'm staring at a circuit, this is what I'm doing in my head. Very cool.
Well, 200 over 1K is 1/5, and 1/5 of 20 is 4.
Nice. Notice that we never had to use the milli
So VR2
button on the calculator. Very cool.
is equal to R2 over RT times E, which is 330 over 1K times 20, and that is equal to, we get it on here, 330 divided by 1,000 times 20, and we get 6.6.
Man, that is so
We know
cool.
it's going to work out the same.
I love that he's doing
but
both.
Because I'm a teacher, I'm going to go through it anyway. R3 over RT for VR3 times E, which is 470 over 1K times 20, and that will equal... Nobody spoil this now.
Love that he doesn't have to hit the milli button.
9.4.
All right.
Okay?
I'm going to stop right there. So, man, there's so much cool stuff here. The milli button. The not having to use the milli button. in the second way, which frankly, awesome. Right, this second way here, you never actually calculate what the current is. It never shows up. All you're asking about is how much voltage is across each resistor. Man, so many cool things. The number choices, love it. All right, you guys, well, have a great day. It's a snowy day here in Minnesota. Hope you're enjoying your day. And remember, physics teachers are awesome.